Hello, and welcome back to Cosmic Whispers. It's a pleasure to have you here with us. Perhaps you're listening to this in the quiet of the evening, or maybe it's your companion on a long drive. Wherever you are, let's take a moment together. Let's pause and consider the sky above us. We often look up and feel a sense of permanence, of stillness. But what if that's an illusion? What if the vast, dark ocean between the stars is, in fact, a highway? What if the universe is constantly in motion, with messengers passing by our little island of a solar system, unseen, in the dark? And what if, just now, we finally built a lighthouse bright enough to spot one? Not just any messenger, but a colossus. A visitor carrying secrets from a star so far away, its light has not yet reached us. Tonight, we are not just telling a story of astronomy. We are telling the story of a discovery that, for a fleeting moment, connected us to the greater galaxy. We are here to talk about an object that broke every rule, shattered every record, and came to us from an unknown home, traveling for longer than life has even existed on our own planet. This is the story of 3I Atlas. Our story begins in one of the quietest, darkest, and driest places on Earth, the Atacama Desert in Chile. Here, the air is so thin and free of moisture that the barrier between our world and the cosmos feels almost non-existent. In this desolate landscape stands a silent guardian, a robotic eye whose official name is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This telescope's job is not one of gentle academic curiosity. It is a sentinel. Its gaze sweeps across the vast southern sky with a programmed, urgent rhythm night after night. It is hunting for threats. It looks for the faint glimmers of light that might signal a dangerous rock, an asteroid on a collision course with Earth, a potential end to civilization as we know it. It is a watchman on the wall, looking for existential dangers. But on one particular night, that robotic eye caught something that wasn't on its list. It found something that wasn't a threat, but a mystery. It detected a faint, unassuming dot of light, moving almost imperceptibly against the fixed backdrop of distant stars. This happens thousands of times a night. The system software dutifully tracks the dot, calculates its path, its orbit, its speed, and prepares to file it away. And then the system faltered. The calculations didn't make sense. This dot of light, it wasn't behaving like anything born of our solar system. It wasn't just an anomaly. It was an impossibility. Think of our solar system as a vast, flat whirlpool, or perhaps a spinning vinyl record. The sun sits at the center, and all the planets, all the asteroids, all the comets we have ever known, orbit in roughly the same direction, on the same flat plane. This is the ecliptic. It is the cosmic riverbed carved by the formation of our system, and everything born here flows along with that current. This mysterious visitor, however, was swimming upstream. It was cutting across our cosmic neighborhood at a severe, defiant angle, completely ignoring the established flow. Its trajectory wasn't just unusual, it was alien. The mathematics was clear. This object was not following any orbital path that could keep it bound to our sun's gravity. It wasn't a leaf caught in our stream. It was a vessel from another river entirely, one that was merely passing through on its way to an unknown destination. Within hours of that first detection, the Discovery team knew. They understood the gravity of what they had found. While most of the rocks Atlas tracks are cruising along at speeds we can comprehend, thousands of miles per hour, this object was blazing through the void at a velocity that seemed to belong to science fiction. The implications hit the astronomical community like a thunderbolt. If the math was correct, they were looking at only the third confirmed visitor from interstellar space in all of human history. The first, as many of you may remember, was the bizarre, cigar-shaped mystery named Oumuamua in 2017. It confused and fascinated us, sparking fierce debates about its nature. The second was Comet Borisov in 2019, an object that, while clearly from another star, at least had the good grace to behave like a comet. Both of those discoveries had fundamentally changed our understanding. They proved that the space between stars is not empty. It's a highway. But this new arrival, this third messenger, was different in a way that made even the most veteran astronomers pause and catch their breath. While Oumuamua had been roughly the size of a football field, and Borisov comparable to a city block, the very first, tentative estimates suggested this newcomer dwarfed them both. We were, potentially, looking at an object several miles across. A flying mountain, carrying ice and rock from a star system so impossibly distant that we may never even know its name. The Chilean telescope, in its nightly vigil against doomsday, had accidentally opened a window, not just into our backyard, but into the deep cosmos. Within 72 hours, the entire world was turning its gaze. Observatories across 6 continents, from the peaks of Hawaii to the mountains of Spain, began to swing their massive instruments toward that same single patch of sky. A desperate, global race against time had begun. Every observatory director, every PhD student, every astronomer knew that this was not an object we could visit. It was a postcard from an unknown sender, and they had to read every photon of light it offered before it vanished, forever, back into the outer darkness. Imagine, if you will, standing next to a highway where the cars are not just cars, but flashes of lightning. That is essentially what astronomers discovered when they refined the calculations for our interstellar visitor. The most shocking revelation was not that it was from another star, but the sheer, mind-bending violence of its journey. This object wasn't just fast by the standards of space, which are already vast. It was moving at 36 miles, every single second. Let's try to anchor that number. At 36 miles per second, you could travel from New York City to Los Angeles in less than 2 minutes. A journey that takes a modern airliner 6 hours would be completed before you could finish this sentence. This measurement didn't just cause ripples. It sent a shockwave through the entire scientific community. It shattered every previous record for an interstellar object. Oumuamua, which had already impressed everyone, was clocked at 16 miles per second. Comet Borisov managed a respectable 20 miles per second. This new visitor was traveling nearly twice as fast as anything we had ever seen from beyond our solar system. What makes this speed so profoundly remarkable isn't just the number itself. It's the story that velocity tells. Like a detective examining the trajectory of a bullet, astronomers can read the history of a cosmic wanderer through its speed and direction. The faster an object moves, the more energy it took to accelerate it. The faster it moves, the more violent the event that must have launched it into the void. This object hadn't just been gently nudged out of its home system. It had been flung. It possessed such tremendous force that it had achieved what scientists call a hyperbolic velocity. Let's break that down. Imagine standing on Earth and throwing a ball. You throw it, it comes back. You throw it harder, it goes higher, but it still comes back. But if you could, somehow, throw that ball at 7 miles per second, it would escape Earth's gravity and never return. Now, apply that to the sun. This comet had been thrown from its home system so hard that it not only escaped its own star, as gravity, but it had enough leftover speed to cruise across the galaxy, encounter our sun's massive gravity well, and fly right through it without even being significantly slowed down. The energy required for that is mind-boggling. It suggests our visitor was a survivor, a refugee from a cosmic catastrophe of truly extraordinary proportions. This incredible speed also meant that our time was desperately short. Unlike the asteroids in our own belt, which orbit our sun for billions of years, giving scientists decades or even centuries to study them, these interstellar visitors are like cosmic shooting stars. They flash through our neighborhood and are gone. At 36 miles per second, this object would cross the entirety of our solar system, a space billions of miles wide in less than 2 years. It would only be within effective range of our most powerful telescopes for a matter of months. Around the world, observatory directors began emergency scheduling sessions. Precious, long-planned projects were shelved. Every single hour of clear night telescope time became a resource more valuable than gold. Every captured frame, every spectrum of light, could hold a clue that might never be available to humanity again. The astronomical equivalent of a gold rush was on, with hundreds of researchers racing to stake their claim on a piece of this ancient wanderer before it disappeared, once more, into the void between the stars. The speed was the first clue, but the mathematics of its trajectory held an even more startling revelation. The numbers, written in the cold, pure language of orbital mechanics, told a story that seemed almost too incredible to believe. When astronomers took the object's speed and direction and traced its path backward through time, they discovered something that left even the most stoic space scientists speechless. This object hadn't just wandered in from the Oort cloud, the icy shell at the very edge of our own solar system. It had crossed the vast emptiness between star systems, traveling for potentially millions, or even billions, of years through a cosmic desert where we thought nothing should be able to survive intact. The proof lay in a single elegant mathematical concept: orbital eccentricity. Think of eccentricity as a cosmic ID card. It is a single number that reveals an object's true nature and origin. An eccentricity of 0 is a perfect circle. Our Earth's orbit is very close to this. An eccentricity between 0 and 1 is an ellipse or an oval. This describes all planets and asteroids bound to our Sun. An eccentricity of exactly 1 is a parabola. This is the perfect knife-edge path of an object that has just enough speed to escape the Sun's gravity, but no more. It will never return. An eccentricity greater than 1 is a hyperbola. This is the path of an object that is not just escaping, but is blasting away with speed to spare. This number is the definitive fingerprint of an interstellar visitor. Oumuamua registered an eccentricity of 1.2. It was just over the line, barely interstellar. Comet Borisov measured 3.6, a number that clearly established its alien origin. Our mysterious new visitor scored an eccentricity of 6.2. That number might sound modest, but in the language of orbital mechanics, it is an explosion. It is the most hyperbolic trajectory ever recorded for any object in our solar system. It meant this visitor was, without any shadow of a doubt, more clearly and definitively interstellar than any object we had ever seen. The mathematics revealed an even more startling truth. When the scientists ran the orbital calculations in reverse, projecting its path back through the galaxy, they found it had entered our solar system from the direction of the constellation Sagittarius. This wasn't just random wandering. The visitor had followed a precise trajectory across the galaxy, threading the needle between the gravitational influences of countless stars, its path a straight line carved through spacetime. Of course, proving this required more than just the initial orbital math. Scientists had to be certain. They needed to confirm, definitively, that our Sun's gravity could not possibly capture and hold such a fast-moving object. The calculations were run, and they were conclusive. Even if this visitor had passed directly through the Sun's fiery corona, absorbing the absolute maximum gravitational acceleration our star could provide, it would still possess more than enough velocity to escape our entire solar system and continue its journey. The confirmation process resembled a kind of cosmic forensics. Observatories worldwide, now fully mobilized, contributed their own precise measurements of its position and velocity. Each new data point was added to the model, building an increasingly detailed and high-fidelity picture of the object's path. And every single new observation strengthened the case. We were witnessing something unprecedented, the fastest, most energetic, and most unambiguously alien interstellar object ever detected. Within weeks, the gatekeeper of cosmic names, the International Astronomical Union, made it official. Our visitor received its designation, 3I Atlas. The 3 marked it as the third confirmed object of its kind. The Atlas honored the telescope system that found it. And the I? The I stood for interstellar, a simple letter that, in this context, carried the profound weight of our cosmos. The mathematical proof of its alien origin was now settled. But the object's physical size, that would prove to be even more remarkable. If you could somehow stand next to this interstellar giant, the experience would be like an ant facing a skyscraper. The early estimates of its size, which had already caused a stir, began to solidify. Our cosmic visitor measured somewhere between 6 and 12 miles across. To truly grasp the difference in scale, let's return to our previous visitors. Imagine Oumuamua, that first mysterious messenger, as a football field, a large object, to be sure. Now imagine this new arrival, 3I Atlas, as an entire city, complete with suburbs stretching out beyond the horizon. It was a true colossus. This size calculation required detective work worthy of science fiction. We cannot, of course, physically measure objects that are billions of miles away. So, astronomers had to use light itself as their ruler. The process is a careful art. By analyzing precisely how much sunlight the visitor reflected, and then comparing that brightness to its immense distance from both the sun and the earth, scientists could estimate its total surface area, and from there, its approximate size. The Hubble Space Telescope, turning its powerful, unblinking eye from orbit, provided the crucial measurements. It captured what was, at the time, the sharpest image ever taken of an interstellar object. The picture that returned to Earth was breathtaking. It revealed something that looked like a cosmic teardrop. At its heart was a bright, pinprick nucleus, the solid object itself. But this nucleus was surrounded by a vast, glowing envelope of dust and gas. This fuzzy atmosphere is called a coma, and it stretched across thousands of miles of space. Hidden within that ethereal glow was the solid core, a mountain of ice and rock that had traveled across the galaxy. What makes this immense size so significant isn't just the impressive dimensions. It's what that size implies about its journey. Larger objects can survive interstellar journeys that would completely destroy smaller wanderers. Have you ever wondered what the space between the stars is really like? It is not empty. It is filled with a constant, invisible rain of high-energy cosmic radiation. It's like a relentless, microscopic sandblasting that slowly but surely erodes anything exposed to it. Over millions of years, drifting alone in that hostile void, this invisible bombardment can wear away entire mountains of ice and rock. A smaller object might be flayed, cooked, and ultimately destroyed. But our visitor's substantial bulk meant it had endured. Its own mass was its shield. The outer layers might have been battered and stripped away during its long, lonely journey, but enough material remained miles deep to protect its interior. And it was this protected interior that was now, finally, beginning to see the light of a new star, our sun. Every grain of dust streaming away from that nucleus represented pristine, ancient matter. Matter forged in an alien star system, now, for the first time, mixing with the particles from our own sun's domain. The size comparison also whispered something terrifying about its origins. To eject something this massive from a planetary system requires an almost unimaginable amount of energy. We are not talking about a gentle nudge. We are talking about gravitational slingshots involving planets far larger than Jupiter, or perhaps stellar explosions powerful enough to hurl city-sized chunks of ice and rock clear across interstellar distances. But its size alone couldn't explain why this visitor felt so special. Its true value is held in a single concept: its profound rarity. We live in an age of abundant discovery. We find new planets, new stars, new galaxies every day. But discovering one of these cosmic messengers? That is like finding a needle, not in a haystack, but in a universe-sized haystack. Consider for a moment the staggering improbability of what we were witnessing. In all of human history, with thousands of years spent watching the skies, charting the stars, building myths and sciences. We had, at this point, confirmed the existence of exactly 3 objects that originated beyond our solar system. 3. That as fewer interstellar visitors than the number of human beings who have physically walked on the surface of the moon. This profound rarity makes each detection a scientific event comparable to discovering a new continent. The numbers tell a story of cosmic loneliness. Our galaxy, the Milky Way, contains over 400 billion stars. We now know that many, if not most, of them host their own planetary systems. Logic suggests that these systems should be constantly ejecting comets and asteroids into interstellar space, creating a steady, invisible stream of wanderers between the stars. Yet in practice, finding these nomads requires an extraordinary alignment of luck, timing, and technology. Think of interstellar space as that vast, dark ocean again, and our solar system is a small, sunlit patch of shoreline. For most of human history, we've been sitting on this beach with our backs to the water. Now, we've finally turned around and built a few lighthouses, our powerful survey telescopes. Most of the ships that pass in the night are still mist. They are either too small, too dark, too far away, or they happen to be moving through a patch of sky that our telescopes aren't monitoring at that exact moment. The fact that we've suddenly spotted 3 in just a few years, Oumuamua, Borisov, and now Atlas, suggests that thousands, perhaps millions more, have passed through our neighborhood completely unnoticed. Each confirmed detection is a breakthrough, a testament to our growing observational capabilities. Oumuamua was discovered by the Pan-STARRS telescope in Hawaii, a system specifically designed to scan large areas of sky for moving objects. Comet Borisov was found by an amateur astronomer, Gennady Borisov, using equipment that, just decades earlier, would have been impossibly expensive. And our newest visitor, 3I Atlas, was caught by the Atlas system, a network of telescopes dedicated to protecting Earth. This rarity also creates a profound sense of urgency. Unlike a planet or a star, which will remain visible for centuries, interstellar visitors offer only a brief, fleeting window for study. By the time we detect them, they are already racing toward us at speeds that make any extended observation impossible. Scientists have perhaps a few months, or if they are lucky, a year or 2 to gather all the data they possibly can. Data that might not be available again for decades. This scarcity transforms every measurement into a precious scientific currency. Each photograph, each spectroscopic analysis, each faint radar bounce represents an irreplaceable piece of information about the conditions in an alien star system. We are, in effect, conducting archaeology on an object that has preserved a pristine sample of an environment billions of miles from home. An environment that we can never, ever visit. And these 3 visitors were not created equal. Oumuamua remained a mystery, possibly an asteroid-like object, perhaps something stranger. Borisov behaved like a typical, if alien, comet. Our newest arrival, 3I Atlas, was proving to be something else entirely. Where Oumuamua had been a riddle wrapped in a cosmic mystery, this new visitor was writing its autobiography in light. The contrast between our guest, 3I Atlas, and its famous predecessor, Oumuamua, could not have been more dramatic. Oumuamua had frustrated scientists. It revealed almost nothing about its true nature. As it looped around the sun, it showed no signs of the gas and dust emissions that characterize normal comets. Its surface remained stubbornly inactive, offering few clues about its composition or origin. Even its bizarre, elongated shape sparked debates that continue to this very day, with some hypotheses stretching into the realm of the extraordinary. This new arrival was the complete opposite. It was a cosmic exhibitionist. It was putting on a spectacular show for anyone with a telescope pointed in the right direction. Within days of its discovery, observers detected the telltale signs of cometary activity. A fuzzy, glowing atmosphere. The coma had already formed around its solid nucleus. A faint tail was beginning to develop as its ancient ices, frozen for eons, were finally being warmed by our sun. The difference was like comparing a locked vault to an open book. While Oumuamua had kept its secrets hidden beneath a mysterious, reddish, and inert surface, our new visitor was actively sharing samples of its interior composition with every passing day. Each puff of gas, each stream of dust particles, represented direct, physical evidence of the conditions in an alien planetary system. Spectroscopic analysis, the art of reading the chemical fingerprints in light, revealed water vapor, carbon compounds, and even complex organic molecules streaming away from the nucleus. These weren't just random chemicals. These were the very building blocks of worlds, and they told a story about the star system where this object originated. The presence of water suggested it formed in a region cold enough for ice to condense. The organic compounds hinted at chemical processes remarkably similar to those that occurred in our own solar system's early history, the very processes that may have led to life on Earth. The behavioral differences were just as striking. Oumuamua had accelerated mysteriously as it passed the sun, a tiny push that couldn't be explained by gas emissions, leading to wild speculation. Our current visitor, 3I Atlas, was accelerating in exactly the way a comet should. Its path was changing in accordance with predictable patterns, matching computer models of ice sublimation and dust emission. It was behaving. Even the timing of its discovery was a gift. Oumuamua had been discovered while it was already leaving our solar system, a cosmic hello, goodbye. Scientists had only a few precious weeks to gather data before it faded beyond the reach of our telescopes. This new arrival was spotted while it was still approaching us. We had months to prepare, to coordinate, to watch it brighten and become more active as it neared the sun. The communication difference was perhaps the most significant. Oumuamua had whispered its secrets so quietly that many remain, and may forever remain, unknown. This visitor was practically shouting its story across the electromagnetic spectrum, and every molecule streaming away from it carried a message, written in the chemical alphabet of an alien world. Scientists analyzing the comet's emissions were like forensic detectives, examining evidence from a scene billions of miles away and millions of years in the past. Each type of gas, each specific kind of dust particle, revealed the precise conditions that existed when this object first formed around its distant parent star. The chemical fingerprints were, quite literally, extraterrestrial. They were offering us our first detailed look at matter forged in an environment completely different from our own. The spectroscopic data painted a fascinating picture of alien chemistry. Water vapor, as expected, dominated the emissions. This confirmed that, like our own comets, this visitor was a dirty snowball, formed in a region cold enough for ice to condense and survive. But this water wasn't alone. Scientists detected carbon monoxide, carbon dioxide, and a rich variety of organic compounds. This suggested a complex, rich chemical environment during its formation. Think of these molecules as a form of cosmic DNA. They carry information about their birthplace, encoded in their very structure. The ratio of different water isotopes, for example like heavy water versus light. Water can reveal the temperature and pressure conditions where that ice originally crystallized. The specific types of organic compounds provide clues about the chemical reactions that were common in that distant planetary system. What made these detections so extraordinary was their clarity. When we study exoplanets, we are usually glimpsing their chemical signatures through a filter. We watch as the planet passes in front of its star, and we try to deduce the composition of its atmosphere from the tiny fraction of starlight that passes through it. It's a diluted, difficult signal. This was a direct sample. The comet was a probe sent from another system, which was now spraying its pristine, billion-year-old interior directly into the mirrors of our telescopes. Every gas molecule and every dust grain was an uncontaminated piece of material from another star system, perfectly preserved in the deep freeze of interstellar space during its million-year journey. This chemical analysis also revealed something unexpected about that journey. The relentless cosmic radiation we talked about, it should have gradually altered the surface composition. Yet the emissions suggested that the material coming off it was relatively pristine, almost untouched. This was more evidence that the object was large enough to shield its own interior, protecting its ancient secrets from the harsh environment of the void. Some of the compounds on the very surface did show evidence of being processed by cosmic rays, creating daughter products or new chemicals that don't typically exist on planets. These radiation-modified chemicals were like a time stamp. They served as a tan line, providing clues about just how long the object had been wandering through the void before it finally, by pure chance, stumbled into our neighborhood. The ongoing analysis resembled a real-time lesson in comparative planetary science. As more and more telescopes, both on the ground and in space, joined the observation campaign, the chemical catalog of this visitor grew more detailed and more complex by the day. As astronomers plotted the visitor's path through our solar system with higher and higher precision, they discovered something that seemed almost choreographed. The cold, impartial mathematics of orbital mechanics rarely produces what we would call coincidences. Yet this object, 3I Atlas, was following a route that appeared, from our perspective, almost designed for maximum scientific impact. Its trajectory would carry it past multiple planets at distances that were perfect for telescopic observation, all while neatly avoiding any close encounters that might use a planet's gravity to deflect its path or change its behavior. Consider for a moment the sheer precision required for such a passage. Our solar system spans billions of miles. The planets are scattered like tiny islands in a vast cosmic ocean. For an interstellar visitor, coming in at a random angle and at a blistering speed, to thread the needle between these gravitational influences while also maintaining a path that was easily observable from Earth, ... The odds of that happening by pure chance seemed vanishingly small. The trajectory offered another remarkable, almost convenient feature: optimal viewing geometry. As the object made its long inbound arc toward the Sun, it would remain visible to telescopes on Earth for months on end. It wasn't scheduled to disappear behind the Sun's glare, nor would it be lost in the daylight sky during its most active and interesting phases. This natural scheduling, this cosmic good luck, allowed for continuous observation during the most critical part of its visit. Even more intriguing was the timing of its closest approach to the Sun. The visitor was projected to reach its perihelion, its nearest point to our star, during the autumn. This is a time when major observatories in both the northern and southern hemispheres would be able to participate in coordinated observation campaigns. Professional and amateur astronomers all over the world would have clear, long nights to get a shot at this cosmic target, right during prime observing season. Its path also provided a natural, large-scale experiment in cometary physics. As the object moved progressively closer to the Sun's intense heating, scientists could watch, in real time, as the ice sublimation ramped up. They could document the dust production accelerating. They could measure the tail as it grew longer and more prominent. It was like having a laboratory experiment on the formation of a comet, but scaled up to planetary dimensions, unfolding right before our eyes. It was ... perfect. Some researchers, perhaps in the quiet of their offices, privately wondered if such ideal conditions could be entirely coincidental. The trajectory seemed almost too convenient, too perfectly arranged for scientific study. Of course, the alternative explanations, that it was anything but a coincidence, entered a realm of speculation that most professional astronomers, quite rightly, preferred to avoid. The orbital analysis, however, revealed one more crucial and sobering detail. This would be a one-time only opportunity. Unlike Halley's Comet, which returns every 76 years, This visitor was on a definitive escape trajectory. It would pass through our system, put on its show, and then depart, never to return. At a distance of 4.5 astronomical units from the Sun, that is, 4.5 times the distance from the Earth to the Sun, out near the orbit of Jupiter, something magical began to happen. At this immense distance, the Sun is just a very bright star in the sky. Yet even here, its weak radiation, accumulating over weeks and months, finally delivered enough energy to awaken ices that had been frozen solid for millions, perhaps billions of years. The process was like watching a time-lapse movie of spring arriving on an entire tiny world. Ancient materials began their profound transformation from solid straight to gas. The physics of this awakening follows predictable patterns that astronomers have studied in countless comets from our own system. Sunlight doesn't just provide gentle heat. It delivers energy in precise packets, or photons, that can strike the molecular bonds holding ice crystals together. When those bonds snap, water molecules and other volatile compounds escape into the vacuum of space. As they burst forth, they carry dust particles along with them, like leaves caught in a cosmic breeze. But this wasn't ordinary ice responding to its familiar, native starlight. These were frozen materials that had formed around a completely different star, under conditions that existed when our own solar system was, itself, still just a swirling disk of dust and gas. This awakening represented a meeting between matter from two separate stellar neighborhoods, separated by distances so vast that light itself takes decades, or even centuries, to travel between them. The process began slowly. At first, just a few molecules escaping per second from the regions of the nucleus that were angled most directly toward the Sun. But as the comet moved closer, as the solar heating intensified, the sublimation rate began to increase exponentially. What started as invisible, ghostly wisps of gas soon became powerful streams, visible to our most powerful telescopes. Those streams then merged into clouds large enough to envelop entire planets. You can think of the nucleus as that dirty snowball we mentioned, the size of a small city, composed of ice mixed with rocky debris and complex organic compounds. As the surface layers vaporized under the new sunlight, they exposed fresh, pristine material from underneath. This created an ongoing, accelerating cycle of sublimation and dust release. The object was, in a very real sense, evaporating before our eyes, losing thousands of tons of its ancient material every single day. This awakening also triggered the formation of the characteristic comet tail. The solar wind, a constant stream of charged particles flowing outward from the Sun, began to push on this newly formed cloud of gas and dust. This interaction created two distinct tails, pointing away from the Sun. One tail was composed of ionized gas, which glowed with a faint blue light in photographs. The other was made of heavier dust particles, which reflected the yellow sunlight. These tails were more than just beautiful. They were visible proof of the ongoing transformation. They were a breadcrumb trail of alien material being laid down across our own solar system. Every photograph captured the object in a slightly different state, documenting this steady, beautiful conversion of ancient alien ice into vast, space-filling clouds of vapor and debris. And it was at this moment, as the visitor was truly coming alive, that the Hubble Space Telescope turned its unblinking eye toward it. What it captured was something unprecedented in the annals of interstellar astronomy. The image that emerged from Hubble's cameras, beamed back to Earth, surpassed every previous photograph of an interstellar object, in both its clarity and its profound detail. Where the powerful ground-based telescopes had shown only a fuzzy, indistinct blob of light, Hubble revealed structure. It revealed features. It transformed our understanding of what, exactly, we were looking at. The image that Hubble returned to Earth was nothing short of revolutionary. The resolution was so precise, so astoundingly clear, that for the very first time, individual details became visible within a luminous, ghostly haze. At the absolute center of the frame, a brilliant, pinprick point of light marked the location of the solid nucleus. The actual rocky ice core remained tantalizingly hidden, veiled within its own shimmering, self-generated envelope of gas and dust. But flowing outward from this central beacon were coherent streams of material, like frozen fireworks captured in a single silent moment. Each tendril, each wisp, told a story of the complex and violent forces that were now actively shaping this ancient wanderer. The most immediately striking feature, visible to anyone, was the overall structure. This was no symmetrical spherical halo, the kind we often see surrounding comets from our own solar system. Instead, 3-Eye Atlas displayed a distinctly asymmetrical teardrop profile. Its tail pointed like a cosmic windsock, directly and definitively away from the sun. This very shape was a visual representation of an ongoing powerful battle, the relentless invisible force of solar radiation pressure, pushing material outward, set against the infinitesimally weak gravity of the nucleus itself, which was struggling to hold its evaporating, disintegrating world together. But Hubble's unblinking orbital eye captured more than just a static shape. It captured something that had never, ever been witnessed before in an interstellar visitor. Clear, unambiguous evidence of active sublimation happening in real time. Visible within the coma, once the images were processed, were bright, focused jets of material. These were not random emissions. They were streaming from specific localized regions on the hidden nucleus, erupting in fountain-like patterns. And as Hubble continued to watch, successive observations showed these jets changing their position and orientation. This was the smoking gun. It told astronomers, definitively, that the object was rotating, turning on an unseen axis. As it spun, different active zones, perhaps fresh patches of exposed ice or geological weak points, would face the sun, heat up rapidly, and erupt like geysers on a frozen world. These jets were the engine of the comet's transformation. This photograph also provided the crucial data needed to refine the object's true size. Those initial ground-based estimates, made from a greater distance and through Earth's turbulent atmosphere, had suggested a true colossus, perhaps 6 to 12 miles across. But Hubble's sharper, clearer vision allowed for a much more precise calculation. By carefully measuring the brightness of the central star-like nucleus and painstakingly separating its light from the overwhelming glow of the surrounding coma, scientists could revise that estimate. The solid core, they now believed, measured somewhere between 1 and 3 miles in diameter. This still made it substantially larger than Oumuamua, a true flying mountain by any standard. But it placed it more in line with the scale of the larger, more substantial comets that are native to our own solar system. Perhaps most importantly, beyond all the data points, the Hubble image served as a historical document. This was, and it remains, the clearest, most detailed view humanity has ever obtained of pristine, physical matter from another star system. It was preserved in exquisite detail, a portrait for future generations to study, to wonder about, and to appreciate. The revelation was slowly sinking in for the entire astronomical community. We weren't just looking at a comet. We were looking at a messenger, a fragment of an alien world, that was carrying physical samples of its home directly to our telescopes. Flowing behind our visitor for millions of miles was its tail, a luminous train that resembled a cosmic wedding veil. But this teardrop shape wasn't just beautiful. It was a detailed physical record of the object's ongoing, violent transformation, written across a canvas of interplanetary space. Have you ever really stopped to think about what a comet's tail is? It's not smoke. It's not exhaust. Every single particle in that glowing, ethereal stream represented material that had been locked deep inside the nucleus for, potentially, billions of years. It was ice and dust from a different star. Now, finally liberated by our sun's heat, it was being scattered across our solar system, a trail of breadcrumbs from an alien world. A spectroscopic analysis of this tail, the art of breaking its faint light into its constituent colors, was like opening a pirate's treasure trove. It revealed a staggering wealth of information about the visitor's birthplace. Different regions of the tail glowed with distinct colors, indicating the presence of specific molecules and ions. Faintly blue sections marked areas where the sun's ultraviolet radiation had struck and ionized gases, like carbon monoxide. The yellow and red regions, in contrast, showed where sunlight was simply reflecting off dust particles of various sizes and compositions. The very structure of the tail also provided clues about the nucleus's rotation and its internal composition. As the object spun on its axis, the active jets we saw in the Hubble image would spray material into space. This created subtle, spiral-like patterns within the tail, very much like the water spraying from a rotating garden sprinkler. By analyzing these faint, curved patterns, scientists could begin to calculate the object's rotation period and even pinpoint the locations of the most active regions on its unseen surface. It's helpful to think of the tail as a fossil record, but one that was being written in real time. The oldest particles, those released weeks or even months ago, had been pushed the farthest from the nucleus by the constant pressure of the solar wind. The newest, freshest material remained close to the source. This created a temporal map, a physical timeline of the comet's activity that extended across astronomical distances. The distribution of particle sizes within that tail told another story, a story about the object's internal structure. The detection of large, heavy dust grains suggested that rocky, gravel-like material was mixed thoroughly throughout the ice. The presence of vast quantities of tiny, fine-grained particles, on the other hand, indicated a different kind of primordial dust, one that had been gently incorporated during the comet's initial formation. This specific mixture, this recipe, revealed intimate details about the environment where the object originally condensed from a disk of material orbiting its parent star. But most remarkably of all, buried deep within this data, was the discovery that some of these dust particles contained organic compounds. These are complex, carbon-based molecules. They had somehow survived not only the initial formation process of their home world, but also the eons-long, radiation-blasted journey through interstellar space. These molecules represented direct, physical samples of the chemistry that occurred in an alien planetary system. Chemistry, perhaps, not unlike that which gave rise to life here on Earth. The tail, it turned out, was essentially a time machine. It was a conveyor belt, carrying information from another star system directly to our instruments, revealing secrets that no telescope could ever hope to detect at such vast, interstellar distances. If you find this journey as fascinating as we do, and if these whispers from the cosmos spark your curiosity, we'd be so grateful if you took a moment to tap the like button, or perhaps even subscribe to Cosmic Whispers. It lets us know that you're here with us, and it helps us continue to explore these profound stories together. As the comet continued its relentless inbound plunge, it crossed an invisible but critical boundary. At a distance of approximately 2 astronomical units from our star, that is, twice the distance from the Earth to the Sun, out in the realm of the asteroid belt, something extraordinary began to intensify. The solar heating, which had been gentle and gradual until this point, suddenly became a cosmic blowtorch. This intense, focused energy transformed our visitor. It went from being a quietly sublimating, slowly evaporating ice ball into a ferociously active, dynamic, and violent comet. It was now producing and shedding thousands of tons of gas and dust every single hour. The transition was breathtaking for astronomers to observe. It was like watching a distant campfire suddenly flare into a raging, uncontrollable bonfire, one driven by forces that operate on planetary scales. The physics behind this dramatic transformation involves far more than just simple heating. Solar radiation, the sunlight itself, carries momentum as well as energy. When billions upon billions of photons, particles of light, strike the comet's surface every second, they physically transfer that momentum to the gas and dust particles. This radiation pressure acts like an invisible, persistent hand, pushing the liberated material away from the nucleus at speeds of several hundred miles per hour. But this process isn't uniform across the entire surface. This is the key. Different frozen materials vaporize at different temperatures, creating a complex, layered choreography of sublimation. Water ice, for instance, begins to sublimate noticeably when it's about 3 astronomical units from the sun. But more volatile compounds, like frozen carbon monoxide or molecular nitrogen, begin to outgas much farther away, out in the cold, dark depths of the solar system. This creates layers of activity that build on each other, intensifying dramatically as the solar heating increases. You can think of the nucleus as that dirty iceberg we spoke of, the size of a small city, floating in the vacuum of space. The sun acts as a giant heat lamp, one that grows more powerful with every passing day. As the outer layers vaporize, they expose fresh, volatile-rich material from beneath, which then vaporizes even faster. This accelerates the process, creating dangerous feedback loops that drive ever-increasing levels of activity. The most dramatic changes, the ones visible from Earth, occur in those localized regions where subsurface pockets of highly volatile materials, like trapped carbon monoxide gas, frozen under immense pressure, suddenly breach the surface. These eruptions create the spectacular jets of gas and dust that can extend for thousands of miles, visible even in high-end amateur telescopes. Each jet represents a geological event, a cryovolcanic eruption, occurring in real time on an object billions of miles away. And as if that weren't complex enough, the solar wind, that constant, million-mile-per-hour stream of charged particles flowing outward from the sun, adds another layer of profound complexity. As this supersonic wind encounters the expanding, fuzzy coma of gas around the nucleus, it creates shock waves and turbulent, chaotic interactions that sculpt and shape the developing tail structures. This entire violent intensification process is what creates the spectacular visual displays that make comets among the most beautiful and photogenic objects in our solar system. What had started just months before as an invisible, faint speck of ice was transforming, day by day, into a celestial beacon, a temporary star visible across interplanetary distances. And so, as autumn arrived on Earth, our interstellar visitor was rapidly approaching the most dangerous, most critical moment of its entire multi-billion-year existence. It was approaching perihelion. This is the name we give to the point of an orbit that is closest to the Sun. This moment represented both the absolute climax of the comet's spectacular display and quite possibly its utter destruction. At its closest, 3I Atlas would pass just 130 million miles from our star. This sounds like a great distance to us, but for an object made of ancient ice, the unshielded heat at that range is intense enough to vaporize rock and melt metal. For a wanderer that had survived the frigid, absolute zero darkness between the stars for eons, this sudden, violent solar encounter would test every aspect of its structural integrity to the breaking point. The approach trajectory resembled a high-stakes cosmic game of chicken. On one side, the sun's immense gravitational force was pulling, trying to capture the visitor, to bend its path, to pull it into a permanent, fiery orbit. On the other, the object's own tremendous, intrinsic velocity, at 36 miles per second, was fighting to carry it past the sun and back into the cold safety of interstellar space. The mathematical calculations were clear. Escape was inevitable. Its speed was simply too great. The sun's gravity would bend its path, but it could not break its will. But the passage would exact a terrible price. As the month of October progressed, the sublimation rate increased exponentially day after day. What had been a gentle stream of gas and dust just weeks before became a raging, blinding torrent of material, flowing away from the nucleus at thousands of miles per hour. Telescopes across the world tracked the expanding coma. It grew larger than the planet Jupiter ... then larger than several planets combined, transforming our visitor into one of the most prominent and brightest objects in the night sky. The intense, uneven heating also triggered spectacular, unpredictable outbursts. Pockets of subsurface ice, long buried and protected, would suddenly heat, flash boil, and explode into space. These events, visible to observers on Earth as a sudden, dramatic brightening in the photographs, represented geological catastrophes on a scale that is difficult to truly comprehend. Each outburst released energy equivalent to multiple nuclear explosions, hurling debris and shrapnel across distances measured in thousands of miles. A good analogy for this perihelion passage is to imagine trying to run through a blast furnace while carrying a delicate, massive ice sculpture. The outer layers will inevitably melt, crack, and boil away. The question is, will the core hold? If the core is solid enough and the passage is quick enough, something substantial might just survive the ordeal. For the scientists watching this all unfold, this phase represented both a triumph and a tragedy. The intense activity made the comet brighter than ever, making it visible to smaller telescopes and providing an unprecedented, overwhelming flood of data about its interstellar composition. Yet every single day of observation brought the visitor closer to the sun, and therefore closer to the point where the sun's own blinding glare would make any further study from Earth impossible. The October passage would be the final test. It would determine whether this cosmic messenger, this piece of another world, would survive to continue its long journey into the outer darkness, or whether it would disintegrate, shattering into countless invisible fragments of interstellar debris, fated to mark the path of yet another visitor who couldn't withstand our sun's fiery embrace. With the comet's path and velocity now known with incredible precision, astronomers began the most ambitious and perhaps most difficult detective work in human history. Their goal, to follow a trail of invisible breadcrumbs back across space and time to find its home. This wasn't just about rewinding its 36-mile-per-second journey. This was an attempt to reconstruct cosmic history. The object itself was likely ancient, perhaps 4 billion years old, a relic from the time its home system was first forming, a contemporary of our own Earth. The challenge was to figure out when it was ejected and where it came from. This required rewinding the motion of every single star in our local galactic neighborhood. It meant accounting for the tiny, complex gravitational influences that had nudged both the comet and its potential parent systems along their separate paths over millions of years. This wasn't simple mathematics. It was computational archaeology. It was an attempt to reconstruct events that occurred back when our own distant human ancestors were just beginning to walk upright on the African savanna. The challenge here is almost impossible to overstate. It's like trying to determine which cloud on the other side of the planet a specific raindrop in your hand originated from. And you have to do it by tracking it backward through a hurricane, after the hurricane has already passed and dissipated. Stars are not fixed points of light. They move. They drift through the galaxy in complex, swirling patterns, influenced by the giant spiral arms, by close encounters with other stars, and by the overall gravitational field of hundreds of billions of other suns. Over millions of years, these tiny, imperceptible influences accumulate into major, life-altering changes in position and velocity. Supercomputers at observatories and universities worldwide began crunching the numbers. They modeled the movement of thousands of nearby star systems, calculating where each one would have been 1 million, 2 million, 4 million years ago, trying to find a star system that was in the right place at the right time to have been the source. The preliminary results were staggering. The backward projection suggested that 3I Atlas had been traveling through interstellar space for at least 4 million years, and possibly much longer. During that immense span of time, it had covered distances so vast that light itself, the fastest thing in the universe, would take decades, or perhaps even a century, to make the same journey. This wasn't just a visitor from a neighboring star system. It was a true time traveler, carrying pristine samples from an era when our own planet was a very different place. Even more remarkable was the realization that, during this journey, our visitor had somehow threaded the needle. It had passed between countless gravitational obstacles. Any close encounters with other stars along the way could have deflected its path, torn it apart, or captured it in a new orbit. The fact that it arrived here intact and on this specific trajectory suggested either a case of extraordinary, unbelievable luck, or that it had traveled from a direction that was relatively empty, a quiet part of the highway, one protected from major perturbations. The search for the origin point began to focus on regions where stellar density was high enough to produce frequent, violent gravitational interactions. These are the cosmic billiard tables of the galaxy, where stars regularly pass close enough to one another to disrupt their planetary systems, exchanging or ejecting planets and comets. These chaotic neighborhoods represented the most likely birthplaces for interstellar wanderers. Some candidate parent systems showed intriguing characteristics. There were ancient red dwarf stars, for example, known for having stable planetary systems. Such a system could have hosted our visitor for billions of years, in a stable, icy orbit before a chance passing star provided the gravitational kick it needed to achieve escape velocity. But this backward tracking also revealed something deeply sobering about the rarity of these detections. We felt special, having found 3 such visitors. But the models showed, with chilling clarity, that for every one interstellar object we managed to discover, thousands, perhaps millions, more likely passed through our solar system, completely undetected. They are too small, too dark, or their trajectories simply don't bring them close enough to our telescopes for us to ever know they were here. It makes you wonder, doesn't it? As you look up at the night sky, what is passing by right now in the darkness? Understanding the journey's start was one thing. Understanding its survival was another entirely. Between the stars lies a desert so vast and so hostile that crossing it represents one of the greatest endurance tests in the universe. Our visitor had spent millions of years traveling through regions where temperatures hover just fractions of a degree above absolute zero, so cold that atoms themselves practically stop moving. It was a realm where deadly cosmic radiation, with no planetary magnetic field or atmosphere to deflect it, bombards every exposed surface, and where the nearest source of heat and light is trillions upon trillions of miles away. This wasn't a quick hop between neighboring worlds. It was an odyssey spanning geological ages. Consider the timeline of this 4-million-year journey. When our comet was first flung into this darkness, our own species, Homo sapiens, did not exist. The entire story of human evolution, from Australopithecus to the modern day, played out during the time it took the single frozen messenger to cross the gulf between its star and ours. The survival challenges it faced were unlike anything terrestrial life has ever encountered. First, cosmic rays. These are high-energy particles, protons, and atomic nuclei, accelerated to near light speed by distant, ancient supernova explosions. They constantly, relentlessly bombarded the traveler's surface. Over millions of years, this radiation would have chemically altered the outer layers, breaking down complex molecules and forging entirely new exotic compounds that exist nowhere else in nature. Second, the vacuum of interstellar space isn't a true vacuum. It is filled with tiny grains of dust and occasional stray gas atoms. At the speeds our visitor was traveling 36 miles per second, striking even a tiny, microscopic dust grain would be like a bullet impact. It was, in effect, driving through a relentless sandstorm at hypersonic speeds, a sandstorm that lasted for 4 million years and extended across light years of space. Finally, temperature. Far from any warming star, the object's surface temperature would have dropped to within a few degrees of absolute zero. At such temperatures, most materials, including water ice and even rock, become as brittle as glass. Even minor impacts, or the internal stresses from its own rotation, could have shattered entire sections of the nucleus, causing it to disintegrate long before it ever reached us. And yet, our visitor had endured. It had survived all of these challenges and emerged, 4 million years later, largely intact. The very fact that it was still here, still a solid object, and still capable of producing gas and dust upon reaching our solar system was definitive proof. It proved that substantial amounts of volatile, frozen materials had survived the interstellar crossing, locked deep within it. This suggested it had an internal structure that provided protection from that hostile, deadly environment. This brings us back to its speed. That 36 miles per second wasn't just a measurement. It was a biography, written in the precise language of physics. For an interstellar object, velocity is its cosmic DNA. It encodes a startling amount of information about the catastrophic events that originally launched it into space and the gravitational history of its subsequent journey. Like forensic scientists analyzing the spatter at a crime scene, astronomers could read the story of our visitor as violent birth in the very precision of its speed and trajectory. Objects do not achieve interstellar velocities through gentle processes. The energy required to accelerate something the size of a small mountain to 36 miles per second demands gravitational encounters of extraordinary, almost unimaginable violence. We are talking about near collisions with massive planets, worlds far larger than Jupiter, or perhaps the shock wave from a nearby stellar explosion. Or, one of the most likely candidates, complex gravitational slingshot maneuvers involving a binary star system, where two stars orbit each other, creating a complex, powerful, and chaotic gravitational field. The speed signature also revealed clues about the stellar environment where this ejection occurred. Different types of star systems produce different velocity fingerprints for their ejected comets. Young, active, chaotic systems with massive planets tend to newfangled objects out much faster than older, more settled arrangements. Our visitor's extreme velocity strongly suggested it originated in a dynamic, perhaps chaotic, stellar neighborhood. You can think of interstellar space as a cosmic highway system, with different speed limits depending on the local gravitational environment. Objects traveling at modest velocities might have come from nearby quiet stars, but high-speed wanderers, like 3I Atlas, could have crossed much larger distances, originating from more exotic and violent locations. The velocity also provided crucial timing information. Faster objects, naturally, cross interstellar distances more quickly. Our visitor's high speed was another powerful piece of evidence supporting the idea that it had been launched from its home system within the last few million years, making it a relatively fresh specimen in astronomical terms. But speed alone wasn't the whole story. The direction of its travel, that line tracing back toward the constellation Sagittarius, added another critical layer of information for pinpointing potential origins. By tracing that trajectory backward and accounting for the known motions of nearby stars, scientists could begin to identify potential parent systems that might have been in the right place at the right time to launch our visitor millions of years ago. The precision required for these calculations is simply staggering. Measuring the velocity to the accuracy needed for this kind of origin tracing meant determining position changes of less than an inch per second across distances of billions of miles. This demanded unprecedented coordination between observatories worldwide and pushed measurement techniques to their absolute limits. Even the smallest uncertainty in the velocity measurement, a difference of just 1 or 2 miles per hour in that 36 mile per second speed, could translate to enormous errors in determining the origin point, placing the source in a completely different stellar neighborhood. And yet, the data held one more secret. Perhaps the most profound of all, it was a secret about the nature and the ancient heritage of our visitor. Deep in our galaxy's thick disk, a sparse, ancient halo of stars that drift far above and below the main, bright spiral arms, something had violently ejected our cosmic messenger into the void. The thick disk represents one of the Milky Way's most mysterious regions. It is populated by stars so ancient, they formed when our galaxy was still young and chemically primitive. These ancient suns follow long, lazy, elliptical orbits, carrying them high above and below the main galactic plane. They are a sparse halo of stellar relics that have witnessed billions of years of galactic evolution. And the chemical analysis of our visitor's emissions provided the crucial clue to this exotic origin. The ratios of different elements detected in the sublimating ice, the specific flavor of its composition, did not match the composition of objects formed in regions like our own solar neighborhood. Our sun and our solar system are metal-rich, but our visitor was different. Its composition suggested formation around a star with much lower concentrations of heavy elements. This was the exact chemical signature astronomers expect from the ancient, metal-poor stars of the thick disk. Think of stellar neighborhoods like different communities, each with its own characteristic chemical signature that reflects its formation history. Stars born in the main galactic disk, like our sun, are third generation, recycling materials from previous generations of stellar explosions. But the thick disk stars formed when the galaxy was younger, before it had time for those enrichment events. This chemical archaeology was profound. It revealed that our visitor was carrying a physical sample from one of the most ancient stellar environments in our entire cosmic neighborhood. The very ice that was now sublimating under our sun's heat had originally condensed around a star that might have been shining when the Milky Way was less than half its current age. This thick disk origin also helped explain the object's unusual trajectory, that steep, inclined path that defied the flat plane of our solar system. Stars in this population move through the galaxy in highly elliptical, inclined orbits that regularly carry them through different galactic environments. This kind of motion dramatically increases the likelihood of the very gravitational encounters that could eject planetary material into interstellar space. But there was a puzzle. Thick disk stars are ancient, and therefore typically much more stable than younger, more chaotic stellar populations. They've had billions of years to settle into predictable patterns, making violent ejection events relatively rare. For our visitor to have achieved its incredible escape velocity from such a system, it must have been the product of an extraordinary and rare gravitational encounter. This moved the needle on the origin theory. The most likely culprit? A binary star interaction, where two stars orbiting each other create a complex, powerful gravitational field. Or perhaps an encounter with a rogue planet or a brown dwarf star, a cosmic wrecking ball passing through that ancient, stable system. This thick disk connection, this ancient heritage, raised the most intriguing question of all, the true age of our visitor. If it had indeed formed around one of these ancient stars, it might represent some of the oldest, most pristine, preserved matter in our entire galactic region. It would be a time capsule, not just from another star, but from another epoch of the universe, carrying the chemical fingerprints from an era when the cosmos itself was fundamentally different. This ancient heritage was written not just in its chemistry, but in the very structure of the object itself. Because across those millions of years of interstellar travel, those invisible cosmic bullets we mentioned had been slowly, patiently, and relentlessly reshaping our visitor's surface, one atom at a time. This cosmic radiation is one of the most persistent and destructive forces in interstellar space. These particles carry enough raw energy to break apart virtually any material they encounter, gradually altering the chemical composition and physical structure of anything exposed to them for long enough. For our interstellar traveler, this radiation bombardment had been constant, 24/7, for its entire 4 million-year journey. Every square inch of its surface had been struck by billions, upon billions of these cosmic ray particles. Each single impact was capable of shattering molecular bonds, altering crystal structures, and creating new chemical compounds that don't occur naturally on protected worlds like Earth. The cumulative effect, over millions of years, is like being sandblasted by an invisible beam that never, ever stops firing. This process creates what scientists call a space-weathered surface. It's characterized by microscopic glass beads, metallic nanoparticles, and heavily damaged radiation-burned crystals. These features serve as a time stamp, a cosmic tan that allows researchers to estimate just how long our visitor had been wandering between the stars. A good way to think of this cosmic ray damage is like geological erosion, like a river carving a canyon, except it operates on molecular scales and is powered by some of the most energetic processes in the entire universe. This radiation sculpting also helps to explain some of the puzzling aspects of the object's behavior. These space-weathered surfaces often develop strange new properties that affect how they interact with sunlight and the solar wind. These altered characteristics could, in turn, influence the sublimation patterns, the dust production rates, and even the overall brightness of the developing coma. The spectroscopic analysis confirmed this. It revealed the telltale chemical signatures of this radiation processing in the form of unusual molecular species and strange isotopic ratios. Some of the compounds detected in the tail could only have formed through this intense cosmic ray bombardment, providing direct physical evidence of the harsh conditions our visitor had been forced to endure. But here is the most remarkable part. The radiation sculpting, this destructive force, had also created a protective crust. Over the eons, the constant bombardment had forged a hard, tough outer layer of processed, radiation-damaged material. This crust, it turned out, was the key to its survival. It had acted as a shield, protecting the more delicate, volatile ices underneath from the very radiation that created it, preserving them in a deep freeze in the dark for millions of years, until they finally arrived in our solar system to be awakened by our sun. And so, this protective shell, this radiation-forged crust that had served as our visitor's armor for millions of years, was now, finally, beginning to fail. It had formed a resilient barrier, a shield that had slowed the penetration of heat and reduced the steady, erosive sandblasting from micrometeorite impacts during its long voyage. But this armor, born of the void, was never meant to withstand the inferno of a star. This protective shell, however, couldn't hide the object's deepest secrets forever. The relentless focused solar heating was doing more than just vaporizing the surface. It was beginning to penetrate, sending thermal shockwaves into the deeper layers. It was, in effect, performing a real-time geological excavation. The sun was now touching, for the first time, pristine materials that had been shielded from all cosmic rays, from any light, for 4 million years. The comet's true, ancient heart was about to be exposed. In the vast, silent darkness between the stars, countless cosmic messengers travel along invisible highways, pathways that we are only just beginning to detect. The discovery of 3I Atlas, this third confirmed interstellar visitor, was not just a triumph of science. It was also the reveal of a sobering, profound truth about the limitations of our own human observation. We felt for a moment that we had opened a floodgate, but the reality is far more humbling. For every single wandering object we managed to spot, it is now believed that thousands, perhaps tens of thousands more, pass through our solar system completely unnoticed. They follow trajectories that keep them hidden in the cosmic shadows, or they move too quickly, too silently, for our fledgling detection systems to track. Have you ever tried to grasp the observational challenges that make these discoveries so difficult? Most of these interstellar objects are small, dark, and unimaginably cold. They reflect virtually no light at all. They are, for all intents and purposes, invisible ghosts. They only become visible to us when they wander close enough to our sun for its heat to begin the process of sublimation, to awaken their frozen ices and create a visible coma. But by the time they become bright enough to see, they are often already moving at such tremendous, blistering speeds that they provide only the briefest of windows for study. The very geometry of detection adds another layer of profound difficulty. Our telescopes, even our most advanced networks, can only monitor limited portions of the sky at any given time. This creates vast, permanent blind spots where objects might pass through our system, from pole to pole, completely unobserved. An analogy we've used before is that of trying to spot highway traffic by looking through a keyhole. But even that is too generous. It is more like being in a pitch-black room, looking through a keyhole at a vast, dark plain and trying to spot a single unlit bicycle that is miles away. We see only the tiniest, most infinitesimal fraction of the cosmic traffic flowing around us. Think of it another way. Interstellar space is a vast, dark ocean, and we are on a small island. Most of the vessels that pass in the night are far beyond our horizon. They travel routes that never bring them close enough to our shore for our observers to notice. Only the rare few, the ones that, by pure chance, pass directly through our little local patch of sunlit water, or that happen to be carrying exceptionally bright lights, have any chance of detection. And the speed factor makes this challenge even more daunting. An object traveling at 36 miles per second, as 3i Atlas was, crosses our entire solar system, a space billions of miles wide, in less than 2 years. If they are discovered late in their passage, Oumuamua, with scientists might have only a few precious weeks or even days to gather all the data humanity will ever get from that object before it fades beyond the reach of even our most powerful telescopes. But recent revolutionary advances in our sky survey technology are at last beginning to change this situation. The sudden appearance of these visitors in our discovery catalogs over the last few years is not a coincidence. It's not that the universe is suddenly sending us more messengers. It's that we have, for the first time in human history, built a net fine enough to catch them. This transformation began with automated sky surveys, robotic telescopes with names like the Catalina Sky Survey, Linear, and ATLAS, the very system that found our current visitor. These represent a fundamental shift in the entire philosophy of astronomy. For centuries, researchers pointed telescopes at specific known targets. These new systems, however, are cosmic security cameras. They photograph the entire visible sky, night after night, looking for one simple thing, anything that moves or changes. Computer algorithms, powered by processing capabilities that would have been science fiction just 20 years ago, then analyze these millions of measurements every single night. They compare the new images to archived photographs, identifying the millions of stationary background stars and flagging the handful of tiny dots that weren't there before, or that have moved. This is combined with a revolution in camera sensitivity. Modern CCD detectors can capture objects thousands of times fainter than the old photographic plates. This increased sensitivity allows our surveys to detect smaller objects at much greater distances, dramatically expanding the bubble of space under our constant surveillance. And perhaps most importantly, the scientific community developed new strategies and new software. They began actively searching for these objects, writing the code needed to instantly identify the strange, hyperbolic trajectories that signal an object is not from around here. Even these sophisticated systems, however, still have limitations. Objects that approach us from the direction of the sun remain completely invisible, hidden in its glare, until they have already passed their closest point and are on their way out. Visitors arriving from regions of the sky that are crowded with the stars of the Milky Way can hide in that dense stellar background, perfectly camouflaged in a harbor of light. The staggering realization that we have, in all of human history, detected only 3 such objects is a deeply humbling one. It suggests that dozens, Perhaps hundreds of others have passed right through our neighborhood, uninvited and unnoticed. Each missed opportunity represents a lost library, a collection of unique scientific data that might have provided irreplaceable insights into the conditions around distant stars. This hidden traffic raises profound, almost unsettling questions. What else might be traveling those cosmic highways, just beyond the fragile reach of our current detection capabilities? Like cosmic ambassadors from distant, unknown worlds, each of our 3 confirmed interstellar visitors brought a dramatically different message about the universe that exists beyond our solar system. A comparison between these wanderers reads like a tale of 3 completely different alien environments, 3 different personalities. First, there was one, Oumuamua. It arrived in 2017 as the ultimate enigma, a mystery wrapped in a cloak of reddish silence. It utterly refused to behave like any known type of cosmic object. It was small, roughly the length of a football field, but its shape was bizarrely elongated. Most confounding of all, it showed a complete lack of visible outgassing, no coma, no tail. And yet it accelerated, pushed by a mysterious, non-gravitational force as it passed the sun. ʻOumuamua was the ultimate cosmic riddle, one that scientists are still to this day trying to solve. Then, 2 years later, came 2I Borisov. Borisov played the role of the perfect interstellar ambassador. It was a comforting, reassuring visitor. It behaved exactly as our theories had predicted an alien comet should. It displayed all the classic characteristics of a comet from our own solar system. A clear, solid nucleus surrounded by a fuzzy, gas-filled coma, a well-developed tail pointing away from the sun, and spectroscopic signatures that matched familiar chemical compositions. Borisov was the confirmation. It told us that comets, as we know them, are likely common throughout the galaxy. And now we have our current visitor, 3I Atlas. This object represents something entirely new, a cosmic giant that completely dwarfs both previous discoveries, all while displaying a level of ferocious activity that surpassed anything seen before. Where Oumuamua was a football field and Borisov was a city block, this newcomer stretched across distances measured in miles. These size differences alone tell fascinating, divergent stories about their origins. Small objects, like Oumuamua, require far less energy to achieve interstellar velocities. This suggests they might be fragments, shrapnel knocked loose by relatively gentle, common gravitational encounters in a settled star system. Medium-sized visitors, like Borisov, could represent the typical comet, the kind that is ejected by the billions during the chaotic, early phases of planetary system formation. But giants, colossi like 3I Atlas, demand mechanisms of extraordinary violence. Their existence hints at catastrophic events in their parent systems, gravitational battles with super-Jupiter planets, or the chaotic influence of a binary star. You can think of these 3 discoveries as archaeological artifacts from 3 completely different unknown civilizations. Each one provides unique, irreplaceable insights. They tell us about the conditions that existed in alien stellar neighborhoods, the physical processes that launched them into the void, and the formidable survival challenges they faced during their long, dark journeys to our cosmic doorstep. Their behavioral differences were just as striking. Oumuamua remained largely inert, a silent, tumbling rock, offering few clues about its composition. Borisov became modestly active, enough for us to confirm its cometary nature. But 3I Atlas, our newest arrival, transformed into a spectacular, blinding light show, generating massive, planet-sized clouds of sublimating material that made it visible to telescopes all across the world. Their velocities, too, revealed another layer of their biographies. Oumuamua's relatively modest interstellar speed suggested it might have originated in our local stellar neighborhood. Borisov's intermediate velocity pointed to a source somewhat farther away. But the extreme, record-breaking speed of 3I Atlas, combined with its trajectory, implied an ejection from a much more distant, dynamic region of the galaxy, like the ancient, thick disk we explored in Part 2. Each discovery, then, was not just a new object. It was a new category of object, a new chapter in the story of our interconnected galaxy. Every single molecule streaming away from our visitor's nucleus carried with it the chemical signature of an alien world. It was a fingerprint forged around a completely different star. The spectroscopic analysis, the act of reading that light, was less like astronomy and more like reading an autobiography, one written in the fundamental language of atoms and molecules. Each detected compound revealed specific, intimate details about the environment where this object originally formed. This is a point that cannot be overstated. Unlike studying distant exoplanets, where we only get to glimpse their chemical signatures as they are filtered through thick atmospheres and contaminated by their own star as radiation, here we had direct access. We had uncontaminated physical samples from another planetary system being delivered, free of charge, directly into our telescopes. Water, as expected, dominated the emissions. But this wasn't ordinary terrestrial water. Isotopic analysis, a deep dive into the flavor of the water molecules, revealed subtle, critical differences in the ratios of heavy to light hydrogen atoms. This isotopic fingerprint is a cosmic birth certificate. It provides direct clues about the temperature and pressure conditions that existed when this ice first condensed around its distant parent star. The carbon compounds added another, richer chapter to this alien biography. The detection of carbon monoxide, carbon dioxide, and various complex organic molecules suggested it formed in a region where carbon chemistry could occur freely. This was likely within a dense, primordial debris disk surrounding a young star. These are the very building blocks of life as we know it, and they had been locked in a perfect cosmic deep freeze for millions of years, preserving the exact chemical conditions that existed when alien worlds were still in the process of forming. We can think of the nucleus, then, as a geological core sample from another star system. As the sun's heat penetrated deeper, it was as if it were drilling down, layer by layer, exposing different epochs of that object's formation. The outer layers, as we know, were scarred and altered by cosmic rays. But the deeper layers, now being vaporized, were pristine, shielded from radiation, and preserved in their original state. The presence of these complex organic compounds was particularly intriguing. It suggested that the chemical processes that occurred in our own solar system's early history, the processes that ultimately led to us, are perhaps not unique. Complex carbon-based molecules require specific conditions to form and survive: adequate time, appropriate temperatures, and, critically, protection from destructive radiation. The fact that they were here in such abundance suggested that our visitor was not debris from a young, chaotic environment. It was likely material from a mature system, one that had been stable for a long time, allowing this complex chemistry to develop. The metal content, the heavier elements detected in the sublimating gases, told yet another story. It spoke of the parent star's metallicity, its generation. It suggested the parent star had been, like our own sun, enriched by the ashes of previous generations of stellar explosions. And most remarkably, as we've explored, some compounds on the surface showed clear evidence of having been processed by cosmic radiation during the interstellar journey. This created daughter products, new chemicals that acted as a time stamp, a cosmic clock that allowed scientists to verify the duration of its long voyage. This chemical archaeology was, in short, providing our very first detailed, hands-on look at matter forged in an entirely different corner of our galaxy. Across 6 continents, in the quiet, dark domes of the world's great observatories, a silent, desperate race against time itself was underway. Astronomers were trying to capture every possible photon of light from our rapidly fading cosmic visitor. The urgency was palpable. It resembled a frantic archaeological dig, but one where the priceless, Unique artifacts were actively dissolving, even as the scientists tried to study them. Every passing day carried 3I Atlas closer to a single unavoidable deadline: solar conjunction. This is the point of its orbit where, from our perspective on Earth, the object would disappear directly behind the Sun. It would be lost in the Sun's blinding glare, completely and totally unobservable for months. And when it finally emerged on the other side, it would be a ghost. It would be racing away from us at its full tremendous speed, growing fainter and fainter with each passing hour, likely beyond the reach of all but our most powerful instruments. This was the final window. Observatory directors worldwide scrambled to reorganize their observing schedules. Long-planned, multi-year projects were unceremoniously canceled or postponed, freeing up precious telescope time to focus on this single, once-in-a-lifetime target. The Hubble Space Telescope, normally booked solid for years in advance, received emergency Director-S discretionary time to capture the highest resolution images possible before the object was lost. Ground-based facilities from the clear, high deserts of Chile to the volcanic peaks of Hawaii coordinated their efforts. They worked together to maintain a continuous, unbroken coverage as the Earth's rotation carried different sites into darkness. When the sun set for one observatory, it was rising for another. It was a massive scientific relay race. Optical telescopes ran their leg, measuring the object's brightness, tracking its precise motion against the background stars. Infrared instruments took the baton, analyzing the heat emission from the nucleus, mapping the temperature variations across its surface. Radio telescopes, vast dishes pointed at the sky, listened for the faint, telltale hiss of specific molecular emission lines, trying to identify the exact composition of the sublimating gases. Think of each observation as a single snapshot of a rapidly and violently changing system. Conditions could alter dramatically from one night to the next. The sudden, explosive outburst events, where the comet would suddenly increase in brightness by a factor of 10, provided spectacular viewing opportunities, but they lasted only for a few days or weeks before fading back to normal. This race against time was further complicated by the simple celestial mechanics of our own Earth's orbital motion. As the weeks passed, the viewing geometry, the angle between Earth, the comet, and the Sun, was constantly shifting. This altered the lighting conditions, affecting which features could be observed. Some measurements were only possible during a few narrow windows of optimal alignment. Weather, a trivial concern for space telescopes, became a critical, agonizing factor for ground-based observatories. Clear skies, normally taken for granted, suddenly became precious commodities. Every single lost night, every passing cloud front, meant irreplaceable data was slipping away forever. But perhaps the most frustrating aspect of it all was the shared, unspoken knowledge that this was a passive act. We were fishing. We were standing on the shore, watching this magnificent vessel from another world sail by, unable to do anything but take pictures, while our current visitor, 3I Atlas, raced towards its fiery appointment with the Sun. Mission planners and engineers were already hard at work, designing the very spacecraft that would intercept the next interstellar wanderer. This time, we would not be passive observers. The European Space Agency, ESA, had been developing exactly such a capability, their Comet Interceptor mission. This is a spacecraft and a concept unlike any other. It is designed not to launch toward a predetermined destination, but to wait patiently. The concept represents a fundamental and profound shift in our entire philosophy of space exploration. For decades, our missions to Mars, to Jupiter, to Pluto were launched toward targets we've known about for centuries. We chased them. The Comet Interceptor, instead, would remain dormant. It would be launched into space and parked at a quiet, stable gravitational balance point between the Earth and the Sun, and there it would wait. It would sleep, perhaps for years, until a suitable new target, a pristine, long-period comet, or ideally, a new interstellar visitor was discovered. Think of it as having a cosmic Coast Guard station, positioned perfectly along the main shipping lane, ready to investigate any unusual, fast-moving vessel that might pass by. The waiting game requires extraordinary patience, but the moment of discovery would trigger a frantic race. The spacecraft systems dormant for years would need to spring to life within days or weeks. It would then need enough fuel and maneuvering capability to launch itself from its parking spot and race to intercept an object with a completely unpredictable trajectory and an incredibly high velocity. Mission designers are facing unique challenges, planning an encounter with an object whose characteristics, its size, its shape, its composition, its activity level, will remain completely unknown until just months before arrival. Traditional spacecraft are specialists, designed for specific targets. An interstellar interceptor needs to be a versatile jack-of-all-trades. It must be capable of studying anything from a tiny, inert, rocky asteroid like Oumuamua to a giant, wildly active, gassy comet like 3I Atlas. The scientific payloads packed onto it represent our wishful thinking made manifest. Instruments capable of analyzing surface composition, peering inside its internal structure, measuring magnetic fields, and sniffing the sublimating gases would all be packed into a platform small enough to achieve the incredible velocities needed for an interstellar intercept. The timing requirements are, frankly, terrifying. From the moment of discovery on Earth to the moment of intercept in deep space, mission controllers might have only a few months to calculate the complex trajectories, upload new navigation commands, and execute the precise engine burns needed to reach their target. The traditional mission planning cycles that normally take years would need to be compressed into a few frantically paced weeks. The ultimate goal is to graduate from passive observation to active, in-person exploration, to transform these interstellar visitors from fleeting, distant curiosities into thoroughly studied, intimately known representatives of alien stellar neighborhoods. Hidden throughout our galaxy, invisible traffic lanes carry the ejected debris of star formation between star systems, flowing in patterns that we are only just beginning to understand. The discovery of not one, but 3 interstellar visitors has revealed something remarkable about the space between the stars. It is not an empty desert. It is a complex transportation network, a web of invisible highways, where cosmic hitchhikers follow predictable routes shaped by galactic gravity and stellar motion. These highways connect every star system in our galactic neighborhood, creating opportunities for the exchange of material, of water, of organics, of the building blocks of worlds on scales we had never before dared to imagine. Computer simulations of galactic dynamics are now showing us how this works. Objects ejected from planetary systems don't just wander randomly through space. They follow long, curving paths, influenced by the overall gravitational field of the entire Milky Way. Like rivers flowing downhill toward an unseen ocean, this interstellar debris tends to concentrate in specific regions, in currents where stellar density and gravitational influences create natural collection points. You can think of our galaxy as a vast, invisible city, complete with cosmic boulevards, winding side streets, and traffic patterns that have remained stable for millions of years. Objects that enter these routes at specific velocities and from specific directions will follow predictable paths that will carry them past numerous other star systems during their long journeys. And our solar system, it turns out, sits at the intersection of several such pathways. This mapping effort is in its infancy. It requires tracking not just the current positions of the stars, but projecting where every nearby star will be, millions of years into the future. These changing configurations are what alter the invisible highway network continuously over cosmic time. Some routes, it seems, are more heavily traveled than others. Regions where binary star systems create complex, chaotic gravitational fields tend to be factories, producing and ejecting far more material than isolated single stars. Stellar nurseries, where young systems are still forming, also generate significant debris flows as their violent, early processes scatter leftover material into interstellar space. This highway concept helps explain why certain types of interstellar visitors seem to be more common. It's providing a roadmap. By understanding where these invisible highways intersect our solar system, astronomers can begin to predict the most likely directions for detecting future visitors, and they can position our next generation of survey telescopes accordingly. We stand right now at the threshold of an entirely new scientific discipline. Ancient artifacts from alien worlds are now arriving at our doorstep, carrying messages from across the galaxy. Each interstellar visitor represents something truly unprecedented in all of human experience, a physical sample from another star system. This is the dawn of interstellar archaeology. Unlike all of astronomy's traditional reliance on passively analyzing faint light from distant objects, this new science provides direct access to the matter itself. Matter forged under alien suns, and matter preserved in a perfect cosmic deep freeze for millions, or even billions, of years. The implications of this extend far beyond simple curiosity. These wandering time capsules carry the chemical fingerprints that reveal the intimate conditions during planetary formation around other stars. They provide ground truth for all of our computer models and theories about how solar systems, including our own, develop and evolve. Think of our solar system as a cosmic port of entry, and we have just hired our first customs agents. Equipped with spectrometers and advanced cameras, they are now, for the first time, examining the cargo from these distant stellar neighborhoods. Every measurement, every detected compound, adds another piece to an enormous, galaxy-spanning puzzle, a puzzle that is beginning to depict the true diversity of planetary environments throughout our galactic region. The archaeological metaphor becomes even more appropriate when you consider the vast time scales involved. An object reaching us today, like 3I Atlas, began its journey when our own planet looked completely different, when our own ancestors were just beginning their story. It carried physical samples from a different epoch, an era when different stars dominated the local galactic environment, and when the chemical composition of interstellar space itself may have been different. The future of this discipline, with missions like the Comet Interceptor, will transform interstellar archaeology from a passive science into an active, hands-on field. These future missions will allow for detailed surface analysis, for sample return capabilities, and perhaps one day, even for the deployment of landers on particularly large or interesting visitors. But perhaps most importantly, interstellar archaeology is revealing the galaxy as a place where material routinely travels between star systems. It is forcing us to accept that we live not in an isolated solar system, but as part of a vast, interconnected galactic community. A community linked by invisible highways, carrying the very water, the very carbon, the very building blocks of life, from one world to another, in a cycle that may be as old as the Milky Way itself. This is a profound shift in perspective. And the dawn of this new discipline promises discoveries that will, without question, reshape our understanding of planetary formation, stellar evolution, and ultimately, our own place in this vast, wandering, and interconnected cosmic neighborhood.